Hello again, everyone. This is Mr. Chappa, and this video is going to wrap up this week's lesson about the Z distribution and the T distribution. Hopefully, you've already watched the first video that I recorded using Zoom about this. If you haven't, I strongly recommend going to watch that first because this video is working under the assumption that you have watched it, and as a consequence, this video is not going to be quite as long as the previous. So let's get started. This video, like the previous one, is being recorded using Zoom because I want to show you some things on my laptop. In the future, however, most videos will be filmed by me standing at a whiteboard, using my phone to make a video, uploading it to YouTube, and then linking that video inside of Canvas. So expect to actually see me doing some teaching standardly, if you will, at a board in future videos. But for this video, I just want to remind you how to use the T distribution. And for our purposes, because I don't want to require everyone to purchase a certain sort of technology, we will be using T distribution tables. Any distribution tables that you're going to need can be found in Canvas under Files. And right now, the only folder there is distribution tables. Over the course of the semester, more files will be made available here. Click on distribution tables. You'll see the chi-square distribution, which you may not be familiar with, because it's not a standard part of statistics. The T distribution, which I'll open in a moment, and the Z distribution, which we used in the previous video. Opening the T distribution will open a PDF, so it should be viewable from most devices. I am going to download it and open it outside of this particular frame. It's still in a tab, but that's okay. It might also open up an Adobe Reader, depending upon the settings of your computer or your device. All right. So for comparison purposes, I want to also open the Z distribution to remind you how it works and show you the similarities and the differences between them. Go to the next file and we'll download it, open it in its own tab. Just a reminder about the Z distribution. The Z distribution gave us the answer to the question, what is the area to the left of a certain Z-score under a standard normal distribution curve? Just a reminder, a standard normal distribution curve is just a fancy way of saying a bell curve. But from a nitpicky statistical perspective, if you ever see the phrase standard normal distribution, that means it is a bell curve with two very specific characteristics. Those characteristics are that the population mean, whose variable is mu, is equal to 0. And the population standard deviation, whose variable is sigma, is equal to 1. And as a consequence, we usually draw a picture that looks like this. The mean on a bell curve is always in the middle, so 0 would be here. And it's not impossible to represent the standard deviation. If any of you have ever had calculus, then you may be familiar with something called an inflection point on a graph. If you haven't had calculus, it's okay. An inflection point on a graph is where a graph switches from being arced upwards, arced downwards, or vice versa. And on the standard normal distribution, there's actually two inflection points, one on the right and one on the left. In a standard normal distribution, that inflection point represents one standard deviation. We're not going to go into the mathematics behind why that would require calculus. And since this isn't a calculus-based statistics class, we just don't go there. So it is technically possible to represent the standard deviation on a standard normal distribution. We usually don't do it though because it involves calculus concepts. So I'm going to get rid of all the stuff that's in red. And the Z curve answered the question, if you give me a Z value like Z equals, we'll say 0.75, and you shade the area to the left of it. And for the Z distribution, it does give you left areas. Your Z chart will answer that. All you have to do is look up the Z's on the left and top edges and then go inside to find corresponding left area. In this particular case, we would go to Z equals 0.75. Remember that the numbers on the left side are the digits to the left and right of the decimal place, and the number on the top is the second decimal digit. So to find Z equals 0.75, we would have to go to the second page where the Z's are positive. Put a 0.7, which would be this row. And then the 0.5 column means 5 in the second decimal digit. So 0.75 would be right here, and the decimal that I just highlighted would represent the area to the left of that. So in this particular case, that area would be 0. I think it was 7734. Is that what it is? A second to go back there. Oh. All right, here we go. Be highlighted. Yes, 0.773. Which if you turn upside down actually spells the word hello if you would have typed it in the calculator. But that's neither here nor there. All right, let's come on, go back to the whiteboard. All right, and just a reminder, what this means in terms of statistics is if you have continuous data that's measured in decimals, whose mean happens to be 0 and standard deviation happens to be 1, then the probability of some z value being less than 0.75 corresponds to that area. But when you talk about probabilities, you usually talk about them as percent, so it'd be 77.34%. So any area under a bell curve can be thought as a percent or as a probability of the value landing in that portion of the number line on the bottom. So what's up with this t-distribution? Why do we have it, and how is it different from the standard normal distribution? Well, the t-distribution is a bell curve, but it kind of is a little bit different than the standard normal distribution. Hold on, folks. The t-distribution is also a bell curve. So what's the difference between it and a standard normal distribution? Well, for a t-distribution, the mean is still 0. However, the standard deviation depends on the sample size. Actually, it doesn't depend on the sample size. It depends on a measurement called degrees of freedom. Now, when the time is right, I'll tell you how to measure degrees of freedom. And the way you measure it varies from situation to situation. But you'll always be given the formula for calculating degrees of freedom. But we're not actually going to calculate the standard deviation of a t-distribution. I'm just saying that it changes from situation to situation. Now, as a consequence of the standard deviation changing, that means that a bell curve for a t-distribution can either be really flat and wide or narrow and skinny. For example, if you have a large standard deviation, whatever large means, then that means that from the middle, you have to go really far out before you hit that inflection point. But if you have a small standard deviation, then that means from the middle, you don't deviate very far before you hit that inflection point. Basically, the smaller the standard deviation, the less likely it is for data to deviate from the center, and therefore it all gets clustered towards the middle. Now, imagine somebody putting their hands on this bell curve here and pressing it inside, and everything in the middle would just go up, and it would look something like this. So we're not going to really be focused too much on what is the standard deviation of a t-distribution. I'm just letting you know that in a t-distribution, it is not always equal to 1, like it is in the standard normal distribution. And as a consequence, we can either get flat, wide bell curves or tall, skinny bell curves like this one. All right, so that's one difference between the normal distribution and the t-distribution. The standard, well, let's just say z and t. That's one difference between the z distribution and the t distribution. But how else is it different, especially in terms of their charts? Well, let's take a look at the charts and the z chart, and we'll see how it is similar to, if I can get this to do what I want it to do, how it's similar to the t distribution and how it's different from. Again, just to remember, the z distribution has the z's on the edges and the left areas in the middle. But let's look at the t distribution. You notice anything different about it? Look at the top. The t distribution is for given right tail areas, not left tail areas. So that's one of the key differences between these two Z discusses what's to the left of a z-score. T discusses what's to the right of a t-score. That's one key difference, left versus right. Key difference number 2. Notice that this top row, 6 numbers, represent the right tail, and more specifically, the area in the right tail. In the z-chart, the areas are all these numbers in the middle. These numbers, all these numbers represent areas to the left of a z-score. In the t-chart, the areas are on the top. So as you can tell, this t-chart is very limited in the areas that it can accommodate. It can represent a right tail area of 0.10, also known as 10%, or 5%, 2.5%, 1%, 0.5%, and 0.1%. So the areas are in a different location. On the t-chart, the areas are on the top. And notice the left column is titled DF. That stands for degrees of freedom. For this homework, you'll be told what the degrees of freedom are, but in future uses of the t-distribution, you'll be given a formula to calculate the degrees of freedom. All right, so right tail areas are on the top. Degrees of freedom are on the left column. So what are all these numbers on the inside? Well, these numbers on the inside are the actual t-scores. Remember in the z-distribution, the z-scores were split up into 2 pieces along the left edge and along the top row. Whereas in the t-distribution, the t's are all up in the middle. So let's go to the whiteboard and come and document some of the differences between the z-distribution and the t-distribution. Second, folks. Morning. Well, that didn't clean up the way I wanted to. 1 second, folks. All right, that's a little bit better. So here's just a real quick synopsis summarizing the differences between the z-chart and the t-chart. That makes draw a red line. All right, so let's just go over real quick. The z-chart uses left area and the t-chart uses the right area. That's pretty easy to remember because on the top of each chart it tells you this. Nothing to worry about there. On the z-chart, the areas are in the inside of the chart, but on the t-chart, the areas are in the top row. It's easy to remember that the areas are in the top row of the t-chart because if you look at the t-chart, it actually says right tail, meaning the area of the right tail is one of these. Let's see, what was number 3? Number 3 was, in the z-chart, the z-scores are split across the left and the top edges of the chart, whereas in the t-chart, the t-scores are inside the chart. And it's important to remember this as you go back and forth between the 2 charts. In the z-chart, the z's are split across 2 digits on the left and then 1 digit on the top, whereas in the t-chart, all these numbers on the inside represent t-scores. And in the z-chart, there are no degrees of freedom, whereas in the t-chart, there's the left column contains the degrees of freedom. And this may seem like an insignificant thing to point out, but it's really critical. And the reason is when you're doing your homework and your test, you're going to have a formula chart that tells you when to use certain things for different scenarios. If you're given a formula for degrees of freedom, that means you have to use a chart that measures degrees of freedom. So if you're doing a problem and there's a formula included for degrees of freedom, you shouldn't use the z-chart. You should either use the t-chart or, as you'll learn later, the chi-square chart. All right, let's take a look at some specific examples of using the t-chart. On the screen, you see 2 bell curves. We can assume that their centers are 0, even though it's not explicitly stated, because we are being asked to find t-scores, and on the t-distribution, the mean is 0. On number 1, we have a right tail shaded in, whose area is 5%, and we have 20 degrees of freedom. If you haven't done so already, I invite you to open the t-distribution chart that I showed you in Canvas go to Files, click on Distribution Tables, and click T-Distribution, and see if you can find what this T value is. Separates that right tail from the rest of the curve. And while you're at it, number 2 is the same thing, except 10% in the right tail with 62 degrees of freedom. So again, pause the video and see if you can find the T values. All right, I'm going to assume that you paused the video, or you're just waiting for me to answer. Let's go look at the T-chart and find our answers. For the first one, we need 5% in the right tail and 20 degrees of freedom. Keep in mind that when you're looking up the area of the tail, you always think about it as a decimal. So at some level, you need to think that 5% as a decimal is 0.05. Remember, to turn a percent to a decimal, locate the pre-existing decimal point in the percent, move it 2 places to the left, and if you need to, use some extra zeros. All right, so let's go find it. 5% in the right tail, 20 degrees of freedom. All right. Mouse is being persnickety. All right, 5% in the right tail, so that'd be the second column, and then 20 degrees of freedom. So we just scroll down until we find the 20, and remembering that we're in the second column, this number is our T-score, 1.7247. 1.7247. 1.724. So that wasn't that hard. Let's try the other one. And again, when you're looking at a percent, but for an area, but you're using your T-chart, you need to think of it as a decimal. 10% as a decimal is 0.10. Or if you didn't want that extra zero at the end, 0.1. So be prepared to look for either one of them as we find the answer to this question. All right, so we have 10% in the right tail, and our degrees of freedom is 62. 10% in the right tail, degrees of freedom, 62. 10% is the first column, and so we need to find 62 degrees. There it is. 1.2954 equals 1.2954. So that wasn't too bad. So what could possibly go wrong? Well, let's try these two. And you might be thinking, well, they're not that different. Each one has an issue. One is more obvious than the other. For number 3, we have a left tail 1%, and the degrees of freedom is 30. And for number 4, we have a right tail of 2.5% with degrees of freedom of 80. I challenge you to pause the video and try to find both of these T values. You will have to do something we haven't done yet, but I think you can probably figure out both of them without me running interference. So go ahead and pause the video, give it a try, and then unpause the video, and then we'll go through that. All right, if you didn't pause the video and try it, you should, because anybody can follow my lead. The question is, can you take the lead on your own? That's what I'm trying to get you acclimated to do, taking your own lead, not just following mine. All right, so what's the big issue with number 3? The big issue should be pretty obvious, but in case it's not, remember that the T-chart, going back a couple of pages, the T-chart uses right areas. And in number 3, we're given a left area, clearly on the left side of the curve. So does that mean we look at the right area? Well, if 1% is in the left, that means the remaining 99% is on the right. But that really won't help us, because if you go look at your T distribution, there is no 99%. I'm going to switch over quick. The right areas start at 10% and go down. So there is no 99% here. I mean, we can't find the T-score? No. It just means that we need to take advantage of some properties of the bell curve. One thing I wanted to point out about the T-scores in the T-chart, which are all in the interior of the chart, they're all positive. And since the middle of the T-curve is 0, all of these T-scores would be on the right. It's pretty evident from our picture that we need a T-score that is on the left of 0. Remember, On the t-distribution, the center is still 0, which means we need a negative t-score. So how do we find it? We take advantage of symmetry. Being a bell curve, it is symmetrical, which means if I were to cut off the right 1% and get its t-score, we would expect these t-scores to be opposites. So if you're looking for a t-score for a left tail, you just look up the right tail, but stick a negative on the t-value. Let's do it. 1% in the tail, 30 degrees of freedom. 1% in the tail, so that would be column number 4, 30 degrees of freedom. Fourth column, row 30, 2.4573. 2.4573. 2.4573. Except it can't possibly be that because this t is to the left of 0 where negative numbers live. But based on symmetry, this t-score should be the same number, just its opposite, and the t-score there is negative 2.4573. So that's issue number 1. If you're using the t-chart for a left tail, look it up as if it were a right tail, and just remember that your t-score is the opposite of what you looked up. Thank you, bell curve symmetry. All right, let's look at this other one. It is a right tail, so we won't have the same problem as in number 3. The right tail area is 2.5%, and our degrees of freedom is 80. If you're paying close attention, you probably saw what's about to happen. But let's find the 2.5% column. That would be column number 3. Remember, even if you're given a percent, you need to think of it as a decimal. So third column and 80 degrees of freedom. Scroll until we find 80 degrees of freedom. 40, 45, 50, 55, 60, 65, 70, 75, infinity. That's an infinity sign. The problem with distribution tables is that they're limited. At some point, you're going to run out of room to put stuff. Now, I technically could have put row 76 through 80 and even beyond, but most t-distributions, at least in the books that I've taught from, once you've gotten to 75, they just throw in what's called the infinity row. What happens to the t-scores, excuse me, as the degrees of freedom get larger, is the t-scores get small. It has to do with the standard deviation getting smaller. But they are limited to how small they can get for a given area. This bottom row is almost like the limiting value of the t-score for a given right-tailed area. For those of you who had college algebra or trigonometry, and maybe you remember graphs with asymptotes, each column is asymptotically approaching a certain value as the degrees of freedom approach infinity. So what does that mean for you? Well, what it means is if your degrees of freedom goes beyond 75, just use what's called the infinity row. I'm going to write that. I'll probably type it over. That is the lesson from this problem. If degrees of freedom exceeds 75, use the infinity row. I'm sure there's a way to type in infinity, but it was quicker for me to type the word infinity than figure that out. All right, so we're at 80 degrees of freedom. We're still in 2.5%. So 2.5%, I believe, was the third column. Yes, it was. We want the infinity row because our degrees of freedom has exceeded 75. And our z-score, excuse me, our t-score is 1.96. 1.9600. Should you write those last two zeros? Well, it's significant to 4 decimal places, so I would write them. All right, so let's review what's happened so far. On the first two, we were given a right tail area, which was one of the 6 areas on the top row of the t-chart. We were given degrees of freedom that were on the t-chart, and all we had to do was find the correct row and column and see where they intersect, locate the t-scores. On number 3, we were given a left tail area, which means we had to take advantage of the symmetry of the bell curve. Look up the corresponding right tail area, which for number 3 was 2.4573, and then take its opposite, again, due to the symmetry of the t distribution curve. On number 4, the issue wasn't the fact that it wasn't the right tail, because it was the fact that our degrees of freedom exceeded 75. And for our purposes, when that happens, we use the infinity row, and we got a t-score of 1.96. I just want to show you a couple of more things, then we're going to wrap this up. The first thing I want to do is show you how to kind of work the t-chart backwards. In the previous 4 examples, which I'll scroll back to quickly, we were given the area of the tail and asked to look up a t-score. We managed to in each case. So backwards is to give you the t-score and ask you to look up the area of the tail, which we have in this picture. Given a t-score of 2.17, what is the area of that right tail? Now, this is not impossible to do with the t-chart, but as you're going to see, we can't get as accurate an answer as we would like. Now, one thing that's missing here is the degrees of freedom. So let's say the degrees of freedom are, second. I had to go back and look at the t-chart to remember which row I was looking at. Let's say the degrees of freedom are 10, and we know the t-score cutting off the right tail is 2.17, and we want to find the area of that right tail. If we're going to work the t-chart backwards, so to speak, we have to start with the information that we know, which is the degrees of freedom and the right tail area. The degrees of freedom still points us to the correct row, so we're going to go to the 10th row in the chart. Well, what do we do with the t equals 2.17? If we go to the 10th row, because of the 10 degrees of freedom, here's the row we're looking at. And remember, in the t-chart, the numbers on the inside, 6 highlighted numbers, are your t-scores. We know our t-score, so we need to look across there and find it. There's one problem, though. The t-score in this picture was 2.17. And so if we go look at the t-chart, I don't see 2.17 across that 10th row. And in fact, it skips right over it. This value is less than 2.17, but as we go to the next value, it's greater than 2.17. So the t-value that we're looking for isn't there. The best we can do is trap it between these two t-values. We'll go back to the whiteboard and just write what I just said. In the df equals 10 row of the t-chart, value t equals 2.17 up there. However, that value is equals something, which we'll look up, and t equals something else. Up, type them in. Quick. Might even take a picture of it, so back and forth. All right. So, back in the text box. All right. So the t-value of 2.17 is not in the 10th row, but it is between t equals 1.8125 and t equals 2.2281. So we managed to trap it. Well, now what does that mean? Let's go back to the t-chart and take a look at it. If the t-score were 1.8125, then the right tail area would be 5%. But if the t-score were 2.2281, then the right tail area would be 2.5%. But the t we're looking for is between these two t's. So what does that mean about the area? It means that the area is between these two values. Write that down. All right. Break here. Since t equals 1.8125 corresponds corresponds to a right tail of 5%, and t equals 2.2281 corresponds to a tail of 2.5%, the best we can say is the area of this tail is between 2.5% and 5%. And that may not seem like a satisfactory answer to this question. The question being, what is the area of that tail? But if we're going to use the t-chart only, this is the best answer that we can give. Is there a way to get a more precise value for the area? Of course, but it would require technology, and since I'm not requiring everybody to have the same technology, we're not going to go there. All right, I think I said there were two things I wanted to say about the t-chart, but this is really it. When you work it backwards, and there will be situations where we have to work it backwards, excuse me, then when we're given a t-value and looking for the area of the tail, the best we can do, unless we get incredibly lucky, the best we can do is trap the given t-value between two t-values in the chart, on the correct row, of course, and then conclude that the area of the tail is between the corresponding areas of those two t-values. All right, that pretty much wraps it up for this video. Keep an eye out on Canvas. I will be creating a homework assignment and a quiz to go with it. If you have any questions, you know how to reach me, and have a good day.